Oh, hello, old friend. It's good to see you. Let's talk about this word, fascination. It describes an unquenchable urge which compels our hearts to quest and be captivated. As long as there are elegant explanations to complicated phenomena, science will never lose its romance. Over the years, I've traveled the world, indulging in my fascination in physics. And now, I find that a new hunger has woken within me. A fiery need to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my titanium physicists. You're listening to the Titanium Physicist Podcast, and I'm Ben Tippett. And now, allez, physique! It's summertime right now, and in the summer, I like to think about fun things. Now, a megastructure is defined as a rigid, artificially constructed structure which is really, really, really large. So, the Great Wall of China is a megastructure. It's over 6,000 kilometers long. Now, anyway, let's talk about science fiction, because one of the fun things about science fiction is the sciencey part of it. Mostly science fiction writers think about space. They think about what will happen when mankind can engineer structures that take advantage of space, objects which are huge, objects which are megastructures, megastructures in space, objects which are wide as a planet. I'm talking about Dyson spheres, I'm talking about space elevators, I'm talking about ring worlds, I'm talking about things which are so big we'll have to change the world to make them. So today on This American Life, we're talking about space-based megastructures. Now, speaking of changing the world, I'm not sure if you're aware, but podcasting has a godmother, and she's the prophet of change. She is an author who has been distributing her writing online, and she's been podcasting since 2004. Her most popular, currently running podcast is called I Should Be Writing. It's a podcast for wannabe fiction writers where the issues which writers encounter are discussed. It's won the Podcast Peer Award and the Parsec Award. She's also been the editor and host of both the Escape Pod podcast, a show where you get to listen to science fiction stories, and she co-founded the Pseudopod podcast, where you get to listen to horror short stories. She even founded the Parsec Awards, an award show for the best science fiction podcast. And she's been nominated twice for the John W. Campbell Award for Best New Writer. Since the days when I was planning the first episodes of Titanium Physicists, I've been looking forward to the day where I could teach her a little bit of physics. Welcome to the show, Mur Lafferty.
Thanks for having me.
So, Mur, you got a new novel out. It's a monster travel guide, The Shambling Guide to New York City.
Yes.
TIE fighters can purchase this from local bookstores or Amazon, and we'll link to the book in the show notes. So, Mur, for you today, I've assembled two of my titanium physicists. Arise, Dr. Jocelyn Reed! Roar! Dr. Jocelyn did her undergraduate at UBC, her PhD at University of Wisconsin-Milwaukee. She's now faculty in the physics department at Cal State Fullerton. She's a specialist in neutron stars. Now arise, Jacob Stump! Ha-ha! Jacob Stump is an aerospace structures engineer who works for a major American defense contractor. He got his engineering degrees from Embry-Riddle Aeronautical University and the Florida Institute of Technology. He's the host of one of the newest podcasts in the Brachylope Media Network, Technically Speaking, where they talk about engineering. Okay, guys, let's start talking about really big space things. The deal with space-based megastructures is that it's fun to go into space, and getting up into space is a possible solution for a lot of mankind's woes. Mm-hmm. And we can go into space already, but there's a problem with going to space using rockets. It's that, essentially, the higher up you want to go, the faster you want to go, the more fuel you have to take with you as you go up. You heard of this before?
Yes.
Yeah. It's kind of like, if imagine the days before there was anything outside your hometown. If you wanted to go on a multi-day trip, you had to bring food and supplies with you in your backpack. But the more food and supplies you brought, the heavier your backpack would be. And so the more calories you would use, and so the more food you would need to go.
Right.
Kind of diminishing returns. And the same goes for rocket travel. You just need larger and larger amounts of fuels to go higher up. So now travelers don't have to bring all of their food with them. Like even if you're hiking on the Appalachian Trail, you can pop in small towns every couple days and get more supplies. And in essence, there's an idea where, in essence, you build a very large structure. You know, you want to get your little ship out into space. You can build a structure which gives your ship energy along the way and keeps you from having to load up your ship with a whole bunch of fuel just to leave the atmosphere. So the first one we want to talk about is space elevators.
Okay.
So space elevators are really fun. It's an elevator that goes up into space. The name is kind of descriptive. The way they're built is pretty fun. They're not actually like towers. You're not building a ziggurat that's 100 kilometers tall.
Maybe we should explain geostationary orbit first. So when we talk about having stuff in a stable orbit around the Earth, the distance the thing is from the Earth will affect the period of its orbit. So this is like one of Kepler's famous laws of planetary motion, and it tells you if you are closer into the thing you're orbiting, your period of orbit is going to be a lot faster than if you go far away. And so there's a sweet spot of stuff orbiting Earth where the thing orbiting will naturally follow a point on the surface of the Earth. So they always stay on top of each other as the thing orbits and the Earth spins. So that's what we mean by geostationary orbit.
So what a space elevator is it's in essence, it's kind of like, you know, if you had a tree fort, you wouldn't necessarily build a ladder up to the tree fort. Sometimes you would have a rope ladder hanging down from the tree fort that you could climb up. A space elevator is not that different. In essence, it's a rope that leads up to geostationary orbit.
Well, it has to go a little bit past geostationary orbit.
Why?
It's basically the total rope from the part close to the Earth to the part at the farthest end is orbiting as a total object in one of these geostationary orbits. So the center of mass is in a geostationary orbit, and so it orbits around and it stays with the bit close to Earth staying fixed above the Earth's surface.
So that means you've got to have a nice counterweight out past geostationary orbit in order to keep your center of mass there.
I think I got it. I'll go build one right now.
Yeah, I like to imagine it in terms of throwing a broomstick. Like you take off the broom handle on the end, and you throw it up in the air so it kind of spins a little bit. You can describe the broom handle's motion in terms of two different things. It's rotation around the central point, right? So it's spinning, but then it flies through the air and falls. And you can talk about the trajectory of the center of mass. So there's rotation around the center of mass, and then the center of mass is also moving if you do this. And you could build a space elevator with a really, really long broom handle if you wanted to. So the center of mass would be in geostationary orbit, and then it would be rotating around the center of mass with the same period that it goes around the Earth, so that as it goes all the way around the Earth, the bottom of the stick is facing the Earth.
So why don't we have one of these?
Good question. Okay, so part of the reason we don't have one of these is that there's a significant amount of force on the string hanging down from orbit, and so you need a material that's really, really strong. And so if you wanted to build one on the moon, you could make it the string out of Kevlar. And then your little elevator could attach itself to the string and get electricity from the ground on the moon and power your way up into orbit. But if you're doing it around the Earth, it's too far. The gravity of the Earth is too strong, and so it requires quite a lot more tension. And so there's only one material that we know of that's strong enough that we could build a space elevator out of.
Carbon nanotubes.
Yeah, if we try and build it with, things that we're used to building stuff out of, it will tear itself apart from all the stresses of the tension that's holding it taut. So that would be bad.
Yeah. And what's really cool is that these carbon nanotubes have been theorized for a long time, and science fiction authors called them carbon monofilaments a long time ago. And the basic idea is just that on a molecular basis, it's very, very strong. It's a really strong molecular structure. And so it can withstand much higher tension than anything else in the world. I think what I heard for a space elevator is that you would only need a carbon nanotube rope about an inch or two thick in order to build your space elevator on. So really just the problem is building it long enough, because we can already build carbon nanotubes. It's just a matter of making enough of them and making them connected.
I guess, I mean, if you think about nanoscale, that's this sort of the scale of atoms themselves. And so even getting from that scale up to only an inch thick is significant amount of building.
Right.
You would need other building materials to actually make it an elevator. Just attaching a weight to the top of a string and saying, yay, we did it, doesn't actually accomplish anything.
Right. Yeah, I mean, that's kind of like the base on which we would build the elevator. We can climb the rope once the rope is aloft. That's the basic idea. But you're right, we would need to build some sort of climbing system, either with a counterweight that actually drops back down to the Earth, or with just an electrically powered climber that slowly climbs from Earth to space. And the really cool thing about it is that with rockets, it becomes easier and easier to change your elevation as you get higher up in the atmosphere. But with a space elevator, it's the same constant effort all the way up. You're not really having to contend with air resistance, especially if you're going slowly. And so you can do it by taking your time. You can really use engines that totally 100% exist already in real life. So we could get huge amounts of material up into space with this method if we just get the string up first.
Once you have a string, you can imagine running some sort of electric source up it so that you can just power a little motor to climb up it, and it doesn't have to be carrying its own energy the whole way. It's just using the energy that it gets from the strand. So that's sort of maglev style transportation up and down the string is one of the common scenarios that you'll see.
Okay.
So space elevators are fun, but they're only kind of the tip of the iceberg for awesome things. It kind of leads into another totally awesome way of getting into space that's a lot more ridiculous and fun. So when we started, I was saying that, you know, a big extended object will have a center of mass, and that center of mass can be in orbit, and then it'll rotate around that center of mass. And if you're not too attached to the idea that your space elevator is stuck at the bottom to one point, you can make essentially a great big hammer in space that's spinning around a center of mass in orbit, but whose handle enters and leaves the atmosphere. A big, 100-kilometer long handle that swings down, almost touches the Earth, and flies back into space. And that doodad's called...
You've been watching the Avengers again, haven't you?
No, it's called a space hook.
Mur, do you know what a bolo is?
Yes.
Okay, so a bolo is a thing that you'll throw that has two counterweights on either end, and when you throw it, there's tension between the two counterweights, and it spins, but the trajectory of the entire bolo is defined by the center of mass of the two spinning objects. So when you throw a bolo, each one of the balls is spinning individually around a center of mass, but if you just plot that center of mass as it travels, it would be the same as if you'd thrown a ball. Well, imagine you have a bolo that is spinning in space, in an orbit. So imagine instead of the moon, we have two moons that are connected by a string, and they're just spinning like a bolo, but they're still orbiting Earth about that center of mass.
Sure.
Well, what you can actually do is you can make an engineered structure where you put this into a low orbit such that one of the ends of the bolo just kisses the atmosphere for a little while. The other end is still well out in space, but one end of it kisses the atmosphere a little bit and then comes back out into space. And we can take advantage of that because we can fly an airplane or a rocket or something and catch on to one end of that bolo and then ride it up into space. So we're using the momentum of the skyhook. We can ride the skyhook up into a higher orbit in space. And the amount of energy that the skyhook has lost because of us grabbing onto it and because it went into the atmosphere is relatively minimal compared to the total amount of inertia that it has. So you can stabilize the orbit with just a little bit of rockets here and there. But it's pretty cool because it allows you to use reusable aircraft to launch large payloads up into space. You could just fly some cargo aircraft up and catch one into the bolo, drop off your cargo, and then go back down and pick up your next load.
But you'd have to kind of build it in space. How would you get it rotating?
Yeah, you definitely have to build it in space. In order to get it rotating, you would have to have each end of the bolo have its own rockets or some sort of propulsion. And then after you get it spinning, you can use that thrust vectoring. That's the term that we use for like fighter aircraft. You can use the thrust vectoring to stabilize its orbit by shooting just a little bit of thrust here and there in odd directions. it wouldn't just be rocks on an end of a string. It would be like a spaceship on the end of a string and a spaceship on the other end of the string.
Jacob, what's a mass driver? Explain what a mass driver is.
So a mass driver is just an electromagnetic railgun. It's like a maglev train, except the one end of the track hasn't been finished yet. So whatever's on the track just flies off. It's actually one of the other ideas for a space superstructure for launching. You know, back in the 50s, Arthur C. Clarke, when he wrote in 2001 A Space Odyssey, theorized that in the future, all space launches would be done in 3 stages. The first stage would be an electromagnetic rail launch, where you have a vehicle that you're bringing up to massive speeds like Mach 5 on an electromagnetic rail. And then that vehicle launches off the rail and goes high up into the atmosphere. And then at a certain point, it separates and it has one portion that's a rocket that continues into space and another portion that's an airplane that comes back down to Earth and collects the next payload to go on the electromagnetic launch track again. So the only difference really between that system and a mass driver is that typically when we say mass driver, we assume that what we're shooting is not going to provide its own thrust afterwards, that it's just going to be momentum that's carrying it after that point.
This is kind of like how CERN works, right? The Large Hadron Collider is basically accelerating stuff electromagnetically to super high speeds to smash it together. But you could also use this to fling stuff off the planet instead of crash it together.
And the reason why we have built something like CERN, but we haven't built something like an electromagnetic launch track, is that particle accelerators can be done in a loop. You can make really big loops, maybe 5 miles long, but if you want to really launch a space shuttle, you're going to need a linear track, and that linear track is going to need to be hundreds of kilometers long in order to really be effective. So it's a much larger structure that would be required.
And also you want to accelerate things that are bigger than protons or whatever. And like in CERN, they go around in a circle, and each time they go around, they get a bit faster. So you build up the speed. But to launch it off Earth, you can't do that. But that would be another way to avoid rockets, because the power is coming on the ground, and then you just fling the thing off.
So none of those particular ways of getting into space are that crazy. I've just learned about one called a launch loop, though, that's totally crazy. And the idea is that it's kind of like a ski lift. So there's going to be a big cord that you're kind of going to attach yourself to. But unlike a ski lift, it's kind of held aloft by its own momentum. So the idea is that you have this long strip, 4,000 kilometers of this metal cord. You know, imagine you take some rope and you throw it. It's going to kind of fly forward, land on the ground. But instead of just throwing it a little bit, you're going to throw it really, really hard. So hard that it comes back to Earth 2,000 kilometers away. And then at the other end, you're going to catch it and turn it around and relaunch it in the other direction. So it's going to fly along a parabolic arc through the atmosphere, and then it's going to turn around and come back 2,000 kilometers, and then you're going to attach the ends of it. So you have one single loop that's going up, you know, it's 2,000 kilometers either way and down, and it's held aloft by its own momentum. And the deal with this is, you know, it can go about to space. You know, you engineer all sorts of things around it. You make it so it doesn't lose energy to friction, so you're always pumping a little bit more kinetic energy into it. But in essence, you can attach yourself onto one end of it the way you do, say, a tow rope on a ski hill, and once you're up into space, life is easy. Crazy!
Did you follow that, Mur?
Totally. Now, see, there's the point where I don't even know what question to ask.
I know.
Sorry.
Can you, I mean, it'll be like bigger than mountains. Can you imagine this great big cord just flinging off into the sky? And then you like tell your grandkids, oh yeah, that thing lands on the other side of North America. And then you can use it to get into space real easy, not like when I was a kid.
Just do your grappling hook up and get carried off like Mary Poppins, except with a giant cable.
So you say it's so easy, but why don't we have it yet? Is it because it would be very difficult to build in the first place, and after that it's easy?
Well, first off, it requires like crazy advanced materials to withstand the kinds of tension and forces. And it also requires like huge amounts of energy investment to get things started. And it also usually requires like really complicated engineering to control it and keep things from going unstable and having like a massive like mountain-sized pile of cable crashing into some city.
Yeah.
Another thing is a lot of these things, they have sort of a lower limit of making a prototype, which is a huge initial step, right? Like with a rocket, you can make a little rocket, you can build up from there. But if you're making a space elevator without, say, going to the moon and making a little prototype moon-sized space elevator, which has its own setup costs. You have to start with something that's pretty huge to even get anything that works as a space elevator. It's a complex system, and you can't build up to it in pieces and really test them until you have the whole thing.
I think the real answer, though, is just the sad reality is that these systems are so expensive that it would require huge international commitments to build them, and it just nobody is willing to do that. It would be like building an underwater train tunnel from here to England. It's definitely possible, but we don't because they're extremely expensive. But once you ignore that fact and just think about with an unlimited supply of materials, an unlimited supply of manpower, and an unlimited supply of capital, what could you build?
Okay.
There's this movie Elysium coming out about a space station. In essence, there's no room left on Earth to, suntan and enjoy a good life. So the rich people all build a space station and go live on that. So one idea is that building things out in space might help us deal with the fact that there is a finite amount of area on which we can live on the Earth. So let's start talking about building things in space that you can live on. Suppose that we've conquered the getting into space part of it. Let's start building things that we can go live on.
Mur, have you seen the preview for this movie?
I have. It looks like if I lived on Elysium, I'd be vomiting a lot. Because isn't the Earth right above your head?
No.
No?
The idea is that the space station is constantly spinning in order to simulate gravity while you're on this circular space station.
But it would have to be big enough that you don't really feel it as a spin. There's this relativity thing is that any acceleration is indistinguishable from gravity on like a small enough scale. So you spinning around, you're continuously getting pushed to keep in the circle, and that feels exactly like gravity would be. And as long as it's big enough that your head and your feet are not feeling different accelerations, you'd walk around on this thing and you'd feel like you were just walking around on a planet, but the acceleration downwards from your perspective is actually a centrifugal force.
There are these rides at the fair.
It's called the Gravitron.
Yeah, Gravitron. You ever been on a Gravitron?
Yeah, but that's not quite what I was talking about. I was more talking about just the visual vantage point of living somewhere where the Earth is above your head by your point of view.
Right.
And yeah, I know you would have gravity, and I know how that would work. I'm just saying, just the optical illusion of I'm about to fall into the Earth would be enough to make me vomit.
So the thing about the movie Elysium is that they use the design of something that a group in Stanford came up with back in the 1970s called the Stanford Torus. And the Stanford Torus had like glass panes on the ceiling that could be shuttered to direct the sunlight into the area. So you wouldn't exactly have a single point light like you're used to. It would be more like having natural sunlight coming in through skylights in the ceiling. And so you would have that all the time, and it would kind of cause the windows in the ceiling to be opaque, and you wouldn't really be able to see through them during the simulated daytime. But then at simulated nighttime, the glass would shutter a different direction and cause the sun to not be reflected through. And then you might be able to see the Earth, depending on if they want that. I'm sure there's windows in the sides where you could see the Earth whenever you wanted, though.
The view is the best part of going into space.
Right.
So these Stanford Toruses are about a mile in diameter. You can imagine making even larger structures, right? Tube shapes are nice because you can spin them around one axis.
Ooh. We should... So have you read Ringworld?
No.
Oh my gosh.
I know
okay.
I know what it's about, but I haven't read it.
So this is just one of the classic science fiction stories of a megastructure. And it starts from the same thing where you just have a ring and it's spinning. But this time, instead of being a mile across, you have the ring covering the whole orbit of the Earth. So it's a ring around the sun at the distance of a planetary orbit.
So it would just be massive. More massive than we could probably comprehend.
So if you wanted to make one, it would take 2 Neptunes worth of mass. So you'd go out and you'd go phone God and you'd say, "Hey God, the solar system according to these specifics," and he would say, "Sure, Ben." And he'd go out and he'd grab Neptune and Uranus and he would smear them out like clay and make a big hula hoop with it. Radius would be about the orbit of the Earth's radius, and then he'd have to spin it. If it wasn't spinning, the system, essentially it's a big rigid hoop. It would be able to kind of not collapse into the sun from its own rigidity, but if it was just sitting there or even rotating once a year the way the Earth does, it wouldn't feel any net gravity. The people sitting on the inside of the hoop wouldn't feel any net gravity, or at least not too much. So you'd have to spin it fairly quickly The greater spin of this hoop is what provides gravity. It's kind of like on the Stanford torus, everybody is stuck to the inside of the ring, and the axis of rotation goes through the center of the sun. So you look directly up, and you'd see the sun at the center.
Okay, and what was the point of the ring world?
It's one of these, like, we ran out of room on Earth, we want more space, and so now you have 3 million times the surface area of the Earth.
Yeah, and in the book, they happen upon it, and they arrive at a time so far past when it was constructed that practically none of the original creators of the ring world are still around. So the only thing you can really assume is that somebody needed the space. But you also have to assume that they had to destroy a ton of planets in order to make the material to make the space. So maybe those planets were uninhabitable.
But planets aren't that good in terms of space. Like a sphere, the ratio of the area on the surface of the sphere to the volume contained within the sphere, it's minimized. So the sphere is if you want to make something that things can live on, the sphere is pretty much the very worst shape you can get if you want things to efficiently live on it.
So for a given amount of mass, if you want to create a bunch of area, the sphere is the worst kind of way to do that. And the other kind of thing of making these kind of macro structures is that one of the fundamental limiting things of what we could do on Earth is we are limited by the amount of energy available. So there's a fundamental limit, and it's set in the sort of the long term by how much solar energy hits the Earth. That's the energy input that we use to do everything that we would like to do. I mean,
so if we wanted to use as much energy as we could, eventually we'd just cover the face of the planet with solar cells and capture as much of the solar radiation as possible, but why not put solar collectors out in space, eh? So then you're like, unless you cover the entire area of the sun somehow with solar panels, there's always going to be a little bit more energy that you can take from the sun. So eventually you're like, hey, why don't we just cover the sun with solar panels and use that to run our dishwashers and dog cleaners and...
Yeah, priorities.
Yeah. Freeman Dyson came up with this idea. He's like, hey, why not capture every single photon that comes off the sun will hit one of these solar collectors? Why not make something called a Dyson sphere, which is a big, rigid, hollow sphere that you surround a star with in order to capture every last bit of energy coming out of it.
And give you lots of precious living space. Because this was before everyone assumed that we just upload ourselves into the internet, and so we needed like physical space for huge civilizations to wander around in.
Right.
But obviously this idea is pretty insane because it would require even more material than a ring world. And so a more realistic way to capture massive amounts of energy from the star would be what they call a Dyson swarm, where it's basically just millions and millions of satellites with solar panels, and you surround the star with those satellites so that it's basically like a constellation. We call our GPS satellites on Earth a GPS constellation of satellites because they surround the Earth in a pretty symmetrical pattern all the way around. And so this Dyson swarm would be a swarm of satellites with solar panels that surround a sun or a star and collect massive amounts of energy from it, but not all of it. And it would be much simpler to create because then you just have to mass produce individual satellites. You don't have to build a space superstructure.
Yeah. So somebody did a calculation to make a Dyson sphere, the big solid one, and they figured out how much usable mass, so mass that isn't gas, in the solar system. And they found 10 to the 26 kilograms. If we made a Dyson sphere with all this matter in the solar system, how thick would it be? And the answer is you could get an 8 centimeter thick Dyson sphere if you put it about the radius of the Earth.
For that's like all the planets combined?
Yeah, that's right.
That's actually bigger than I might have expected.
Yeah.
Ooh, astronomers are looking for Dyson spheres.
Looking for them?
Yeah, like when we look into space and we catalog all the stuff we see, we try and see the signature that what we're observing is not a regular star, but a Dyson sphere.
Okay, how do we see that?
So the key thing is that you would expect something that's a Dyson sphere, it would eventually have the same luminosity as the star it's surrounding, because what you do with the energy is you do whatever your technology civilization wants to do, but you always end up with waste heat at the end of the day. There's a limit on the efficiency of what you do. So you end up radiating away the waste heat from what you've done with all that solar energy on the backside of the Dyson sphere at what turns out to be an infrared temperature for Earth's orbit-sized spheres. So you look around space for stuff that looks like it's infrared radiating object that doesn't fit the parameters of like a really dim cool star, but is some weird huge solar luminosity style structure that would be radiating in infrared. Isn't that crazy?
Cool. That is crazy.
Yeah, so I actually happened to meet last week. There's a professor at Cal Poly Pomona, Matt Povich, who's doing this work. He's actually looking through catalogs for infrared observations that could be Dyson spheres. And apparently, so far, no one's found anything. But
the implications of finding one would be crazy, right? I mean, it would be evidence of not just alien life, but alien life that's so incredibly advanced that they've built basically the most complicated structure that humans can possibly imagine.
Well, that's not actually true, because humans have pretty good imaginations. And one of the other things you can imagine is a civilization that was not only capturing all the energy of a star, but a significant fraction of the energy of a galaxy.
So you would build a structure around a galaxy and capture the energy of multiple stars? Is that the idea?
Or maybe individual structures around a significant fraction of the stars in a galaxy.
Uh-huh.
So you look at galaxies in the nearby universe and you try and find ones that look redder than they should be. Mm-hmm. And that would be evidence of this kind of Type 3 Kardashev civilization is one that is in possession of energy on the scale of its own galaxy.
What would Type 1 and Type 2 be?
So Type 1 is what you can do just absorbing all the solar energy that would hit Earth. So we're not at Type 1 yet. We're sort of we're below Type 1. And then Type 2 is the Dyson sphere. So that's all the energy of a star. And then Type 3 is all the energy of a galaxy.
Wow.
But yeah, so you start thinking about space structures, and then the next thing you know, you're looking for red galaxies to see if there's some enormous galaxy-spanning civilization very far away.
Yeah. I've got one more factoid about Dyson spheres, if you'd like to hear it.
Sure.
All right, so the idea here is there's a symmetry that exists in gravity, which is that if you're on the inside of a big, hollow, perfectly shaped sphere, you can't feel the effects of the gravity from the mass that was used to create that sphere. A classic example is if I dug a hole to the very center of the Earth, when I was at the center of the Earth, I'd feel weightless because the gravity pulling me from one side of the sphere of mass on my left would cancel out the pull from the sphere on the right. And anywhere you go on the inside of a big hollow sphere, you can't feel any gravitational attraction.
It always just cancels out. Like the near side and the far side, they always cancel out. So you just float around inside the sphere without any gravitational pull that signifies that there's this massive thing of matter surrounding you.
So the deal is that if you have a Dyson sphere, it's a big hollow sphere, and while you're constructing it, the components making up your sphere, the different panels, spherical panels that you're putting in place, will all feel gravitationally attracted to the sun. But once you've attached them together in a big rigid hollow sphere, all of their gravitational attractions towards the sun will kind of cancel out. And so the sphere won't feel any gravity from the sun, and the sun itself won't feel any gravitational attraction towards the sphere. And so the sphere is no longer anything like being in orbit around the sun. They'll decouple from one another. So if you had a Dyson sphere and a comet came in and wanged against the Dyson sphere, maybe knocking it a little bit towards the sun, then the Dyson sphere would drift closer and closer and closer to the sun. There are no really gravitational forces keeping the sun at the center of the Dyson sphere.
It's unstable.
It's unstable. Your sphere will end up, hitting the surface of the sun and melting, and then everything will go bad.
Yes. So not only do you have to build this hypothetically huge megastructure, then you also have to actively keep it from going unstable. So maybe that's why we haven't seen them, because whenever advanced civilizations built them, they crashed into the sun and exploded.
All right, that was fun. So thank you, Jocelyn. Thank you, Jacob. You pleased me. Your efforts have borne fruit, and that fruit is sweet. Jocelyn, you get a banana. And Jacob, you get a cantaloupe because it's shaped like a Dyson sphere. I'd like to thank my guest, Mur Lafferty. Mur, thanks for being on today.
Thank you, guys. I learned a lot.
Hooray. All right, TIE Fighters. Remember, her book, The Shambling Guide to New York City, is now in bookstores or on the internet. You should probably go check it out. Incidentally, TIE Fighters, listen, I love the show, and I love hearing from you. Let's suppose you want to interact with us. Why not follow us on Twitter at Titanium Physics, or you can join our Facebook group. And if you'd like to hang out with us and socialize, why not join our online forum? The Brachio Board is a fun place where fans of the Brachio Media Network gather to chat about science and things. If you'd like to send me an email directly to ask a question or propose a topic, email me at barn@titaniumphysics.com. Or if you'd like to tell me nice things, email the fan email thing, TIEFighter, TIPHYTER at titaniumphysics.com. I'm always happy to hear nice things. Okay, that's it for the main part of the show. Remember that if you like listening to scientists talk about science in their own words, you might also want to listen to other shows on the Brachio Media Network. Like the weekly Wienersmith, where Kelly and Zach Wienersmith talk to academics about their research, or Science Sort of, where we talk about science in the news, or our new baby brother podcast, Technically Speaking. It's Jacob's show.
Yay!
All right, they talk about engineering. So editing support for the Titanium Physicist podcast is provided by a gentleman named John Heath. Thanks, John. The intro song to our show is by Ted Leo and the Pharmacist, and the end song is by John Vanderslice. Until next time, my friends, good evening, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
Yeah. I think I can give a generic statement as to why we haven't seen massive advances in space technology in the past few decades, and that's that as the 20th century turned into the 21st century, our technology got more and more complex. It had more and more subsystems to build a single system. And when it gets to a certain point where something is so complex that a single person can't hold all of the details in their head, that we have to develop different ways of thinking about those systems in order to truly understand them and control them. Really, the forefathers of this kind of thinking were Wernher von Braun when he worked on the Apollo program, because the system of the Saturn V rocket was so complex that not even he, who was the designer and really project leader, understood everything about it. He had to have other people that were focused on smaller aspects of it, but he had a top-down view to make sure that everybody else was doing their job and then assume that everybody else knew what they were doing. And so that's what's really happened with a lot of areas of technology. I mean, with aircraft in particular and spacecraft, we're making less and less different kinds of aircraft and single aircraft that can do more things. So where we used to, during World War II, have a fighter aircraft and a bomber aircraft and a reconnaissance aircraft and maybe 3 different types of each of those. Now we have a single aircraft that's a fighter bomber reconnaissance mix. And really the amount of work that it takes to create that complex combination is greater than the sum of the 3 individuals, because now you have to worry about the complex interactions between the two. And with space elevators and sky hooks and launch loops, they are very complex systems, because on a simple conceptual basis, all it is a iron rope that's 2,000 miles long. And while that's something that maybe we haven't made yet. It's certainly not crazy to think that we could. It would just be really expensive, and who's going to pay for it? But the systems that would be required to make it safe and reusable and consistent are things that we haven't yet developed, and things that are too complex for one person to understand. So that's the basic idea.
Do you actually, like, I mean, you still have to get the energy to get the rockets going up there to begin with, for the amount of energy to get the inertia going. So do you actually, like, win out in the end once you factor in how much energy it took to get the thing going?
Well, it's a relatively reusable system, so theoretically, as long as you get a lot of use out of it, then you might be able to make the life cycle costs win out in the end. But you're right; it's going to require a huge initial energy investment.
Yeah, I guess you can also, like, you can refuel whenever one of the stations dips low, so you get some advantage.
Yeah. You could even put a mass driver on the moon and shoot. you could have the moon shoot out some pieces of moon ore and just smack the bolo every once in a while to keep it spinning. You wouldn't even need rocket fuel.
Okay.
Thousands of individual strands of carbon nanotubes would have to be combined in order to make it an inch or two thick.
Is it only thousands?
I don't know. That's just a guess.
Nanotube width.
Millions, isn't it? Nano is e to the -6.
Well,
nano is e to the -9.
9, okay. So tens of millions to get it a centimeter.
Is that how big an actual carbon nanotube actually is? Like, what's the actual width of a carbon nanotube?
Well, it would be a few. It would be maybe tens of nanometers or hundreds, I'm guessing.
Yeah, they're pretty small.
The diameter of an ideal nanotube can be calculated as follows. Blah 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 blah. It looks like it's 4.3 angstroms in diameter. No. What is that A with the little funny symbol?
Angstroms? That's
angstroms
10
is the
to the -7, I believe.
Yeah. Huh.
So
a bunch of them. You need a bunch of them. How about that? Does that work?
You need, like, millions of them, probably. Close to a million.
Yeah. Cool.
And probably in labs we're building, like, I don't know, probably, I'm guessing right now, like tens at a time or hundreds at a time.
There's actually one lab that's produced kind of like a weird liquid powder mixture where you can extract nanotubes by literally pulling them out, and they kind of like form on themselves, like they self-coalesce and they attach to each other. And it forms a visible string, but just barely visible. I mean, like, smaller than the thinnest fishing wire you've ever seen. I can't remember, what the other details of it. Oh, there it is. The process was developed by Richard Smalley and his coworkers at Rice University. So, anyway,